Hello and namaste. In continuation with the complex integration, we are going ahead with the residues, as after making a proper ground with the residues and singularities and poles and all, we have to go ahead with the residues. So in this particular session, we are looking at the introduction of the residues in detail, as well as the evaluation part of the residues, and which we are keeping, or which we are making the ground for the Cauchy's residue theorem. So residues, the coefficient of 1 upon z minus a in the Lorentz series expansion of f of z is known as residue of f of z at z equals to a. Now the Lorentz series expansion about z equals to a is given to us as this, that is f of z is summation of a in z minus a to the power n is moving from 0 to infinity, plus summation of b n z minus a to the power n is moving from 1 to infinity. So we have got here the positive powers, and here is the negative powers of z minus a in the expansion of the Lorentz. Now residue at z equals to a, which is known as the coefficient of 1 upon z minus a, which is also known as b1. This from here, this is b1. If you'll observe here, if you'll take n equals to 1 over here, we'll be getting it here b1 upon z minus a to the power 1, which is nothing but b1 upon z minus a. That means what? B1 is nothing but the coefficient of this particular 1 upon z minus a, which is according to the definition of residues. Now this is what is been given us here, and therefore this b1 is nothing but, because this bn is the coefficient from this Lorentz expansion, which we have got this as the definition, which we have already seen in the Taylor's Lorentz expansion. So b1 is giving us 1 upon 2 pi I into integration c f of z upon z minus a to the power minus 1 plus 1 dz over the curve c. That means nothing but we have got it here, z minus 1, z minus a to the power 0, which is 1, and which is we are going to get it as this. So residue of the function f of z equals to a, or residue at z equals to a, is nothing but 1 upon 2 pi I integration f of z dz. Now evaluation of the residues, we have got two different types of poles actually, and we have to find out the residue at those two types of poles. The poles and how to identify simple pole and a multiple pole or a pole of order m, that we have seen in the previous session. Please do follow the I button so that you can reach to that particular session which we have discussed about the poles and simple and multiple pole. Now residue at the simple pole is nothing but, if f of z has a simple pole at z equals to a, then residue of f of z equals to a, limit z minus a into f of z tending to a. Actually this type of identity you can write down as residue of f of z at z is equals to a is equals to limit z tending to a of function, that is f of z into z minus a. This can also be written. So this is also one of the notation to go ahead and find out. So we are following this particular notation, residue f of z, and this semicolon will give you at what point you have to find out the residue at. Residue at a pole of order m is nothing but, m has a pole of order m. It's given to us as residue of f of z equals to a, or at z equals to a, is 1 upon m minus 1 factorial, limit z tending to a, d to the power m minus 1 upon d z to the power m minus 1 of z minus a to the power m into f of z. We will be going in detail with this different type of examples based on these two evaluations. Now if f of z is minus 1 upon z minus 1 minus 2 into 1 plus z minus 1 plus z minus 2 the z minus 1 the whole square and so on, find the residue of f of z at z equals to 1. Now if you observe here, we have, this is the expansion we have been given, and we have to find out the residue at the point at z equals to 1. So we have at z equals to 1 means what? We should have all the expansion, in the expansion we should have the powers of z minus 1 has been given to us. Yes, we have been given here. So what is the coefficient here? So residue of f of z at z equals to 1, that is coefficient of 1 upon z minus 1 in the Lorentz series of f of z about z equals to 1, and which is got the value over here is b1. Purposely I have taken a very simple example. Just by looking at the series of Lorentz, you can check the residue of the function as minus 1. Another is find the residue at z equals to 0 of f of z is z into cos of 1 by z. Again, this is nothing but this cos of 1 by z is giving us the expansion as 1 minus z square upon 4 to 5. So it's nothing but just a minute. Cos of z is nothing but it's 1 minus z square upon 2 factorial plus z to the power 4 upon 4 factorial minus z to the power 6 upon 6 factorial, and so on. This is an infinite series. So this is the series which we have used it over here, and we have just replaced this z as 1 by z everywhere in the series. So we have got this type of series. After this z, multiplying this z with inside the bracket, we are going to get it in this way. So if you'll observe here, the coefficient of 1 upon z is nothing but minus half. So if you'll observe here, the coefficient of 1 by z is this minus half, which is nothing but the b1 part, or you can say the residue of the function at z equals to 0. Test the singularity of this 1 upon z square plus 1 and hence find the corresponding residue. So this is f of z is 1 upon z square plus 1 is equals to this, which is nothing but z equals to minus I and z equals to I. These are the two simple poles. Why these are two simple poles? Because both of them are repeating only once in the denominator as a root. And therefore residue of f of z at z equals to minus I is limit z tending to minus I of z plus I f of z. So if you'll observe here, the simple pole, the definition, or you can say the thing is nothing but limit z tending to a f of, or you can say here z minus a into f of z. So here in these cases, this a is nothing but minus I. So minus minus becomes plus I. So we have written z plus I f of z, which is nothing but limit z tending to minus I. F of z is this 1 upon z plus I into z minus I. So this z plus I and this z plus I will go from here. You will remain here with 1 upon z minus I. Keeping the value or putting the value of z equals to minus I, we will be getting the residue of the particular function at z equals to minus I as minus 1 upon 2i. Quickly we can go ahead with another part, that is of residue at the point I. Again it is limit z tending to I, z minus I f of z, which is nothing but this is, and we will be getting plus 1 upon 2i as the residue of this particular function at the two different poles, which are simple poles. Again find the residue of the function tan z at z equals to pi by 2. Tan z, z equals to pi by 2 is a simple pole because it's repeating only once over here. So this z equals to, because they have asked us to go ahead with the z equals to pi by 2, and that's the reason. Otherwise this is nothing but tan of z will have so many different zeros, or you can say here. So that means this is nothing but here, but if you'll observe, if I am putting z equals to pi by 2 in the numerator as well, the denominator we are going to get it as 0 by 0 form. That means the L'Hospital's rule we have to get into the existence. That means the differentiation of the numerator and denominator differently. Differentiation of the numerator with respect to z will gives us 1. Differentiation of the denominator, that is cot of z, is nothing but minus cosec square z, and therefore just putting the values of limit as z pi by 2, we are going to get the value as minus of 1 for this particular residue of z, residue of tan of z at z equals to pi by 2. Similarly, find the residues of the function f of z, z square minus 2z upon this, z plus 1 the whole square, z square plus 4 at each point of its pole. Again, poles, to find out poles means to have the denominator equals to 0. After putting the denominator equals to 0, minus 1 is repeated 2 times, it's a pole of order 2, and plus 2i and minus 2i repeated only once. That means they are the pole of simple pole or pole of order 1. So we can have this f of z like this, and therefore it's minus 1, as I've told you, pole of order 2. If it is a pole of order 2, that formula will exist. Please do follow the previous slides for this particular. Here the value of m is equals to 2, and we are just putting the values of m over here. We are going to get it d upon dz, limit z tending to minus 1, d upon dz of this particular function. You have to go ahead with u by v rule. It's a very simple u by v rule. You can just check this out here. After adjusting the terms, you are going to get the answer for this particular limit or particular residue of the function f of z at z equals to minus 1 as minus 14 upon 25. So you have to understand till this point, because this is just by the formula, and after taking this you can have just go on solving this, because it's a d by dz of u by v rule, and then just go on simplifying this limit. You're going to get the answer as minus 14 by 25 for this particular function. Then z equals to 2i is a simple pole. Again, it's because of a simple pole. It is quickly we can go ahead, and it is nothing but z minus 2i f of z. F of z will gives us this. So this is z minus 2i will go from this particular bracket over here and will remain here with this z square minus 2z upon this. Now putting z equals to 2i everywhere in this, so we are going to get in this way, and therefore taking this particular, going ahead with this rationalization of 4i minus 3 multiply divide for this, because we wanted to have it in the simple format, or you can say a x plus iy format of this particular answer, and that's the reason it is 7 plus I upon 25 as the final answer for the residue of f of z at z equals to 2i. Similarly, minus 2i is a simple pole. We can go ahead fast, quickly. You can just pause the video, try to get the answer, whatever I have got it on the screen, that is 7 minus I upon 25. Pause the video, try to get this, the residue of the function f of z at z equals to minus 2i as 7 minus I upon 25. This is about the z equals to 2i as a simple pole. And yes, then this is a self-observation slide which is favorite of mine. Find the residue of f of z at the singular points. 1, 2, 3 questions has been given to you. You can easily find out the residue of the point, residue of the function at the different particular points, and these are the answers provided to you. Hope you will able to solve this particular 3 self-observation slide. If not, please write me in the comment section so that I can provide you the answer. Thank you. Happy learning.